Now, when we begin to deal with surface integrals, these tangents and normals to the surface are going to be very important to us. But we also have to deal with one other issue, which is that we need to be dealing with orientable surfaces. So we want to think about how these gradient vectors or these normals to the surface differ and what happens when the surface is not orientable. So let's consider a given explicit function where z is in terms of x and y. So for example, z is equal to 3x minus y squared. Then we have a function of three variables for determining the gradient. So essentially it's the z variable minus the expression in terms of the other variables. So for, in this case, z minus these two components. So our g function is z minus 3x plus y squared. Now, for this example, the z coefficient is positive, and so this is an upward pointing vector, upward pointing normal vector. Now, this will allow us to point the gradient vector, as we saw in the second section, away from the curve of the graph. So if we wish the gradient to point inward toward the curve of the graph, then we would simply flip this. We would put our z function first and then subtract z at the end, which essentially is equivalent to flipping all of these signs. Now, to check the orientation of your normal vector, you can choose coordinates on the surface that satisfy the original equation and compare the vector obtained to the graph of the surface. So to calculate the normal vector for an implicit function, you may need to check the orientation in the region that you are working with, particularly if there is more than a single z term. But typically, as with the above, allow the dominant z term to be positive, and most cases it will work. If your surface is given in parametric form, typically the standard method for calculating the normal vector produces a vector oriented in the outward direction. So our methods from the parametric surfaces examples don't need to be modified if we want a vector pointing outward. But there will be occasions where you may wish to calculate the flow in the opposite direction. And so in that case, the order of the cross product does matter. So you could switch the order of the cross product, or you can just change all the signs after calculating it in the normal way. You would want to double check to make sure the orientation at a point that you know, somewhere where the gradient isn't zero, is clear and you can visualize that example. Now let's consider calculating normal vectors to the solid, one for each surface bounded by the coordinate plane and the equation z equals 1 minus x minus y, so that we can think about the orientation. So another way of stating the plane to the surface is x plus y plus z minus 1 equals 0. So this has one side equal to 0, so we can make this our g equation. And then grad g will just be 1 plus 1 plus 1. So that's our normal vector to the surface. This is z pointing upward. So this is away from the coordinate planes. And so it's outward from the region. The graph of our surface is a plane with intercepts, I'm missing a comma here, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the coordinate planes forms a kind of pyramid with the peak of the pyramid at the origin. Or it's at the above the origin, or depending on how you want to orient it. To orient the normal vector out of the surface, we want the vector pointing away from the origin. And so in this first octant, so that means all the components of the vector must be positive. We can make this a unit normal vector by rescaling, by just simply having the magnitude of our gradient, which was 1, 1, 1. The magnitude of that is square root of 3, and so just dividing all the components by 3. Now, what about the coordinate planes? Well, the normal vector to the xy plane is either k or minus k. If we don't want it to point upward because that would point into the region. We want it to point out of the region, so we would choose minus k. For the YZ plane, then the YZ plane would have the perpendicular direction to be the X direction, so the I or minus I. And again, we want it pointing out of the region, so we would choose minus I. And then for the XZ plane, it's either J or minus J. And again, we want it to point out of our region. So in this example, we would pick minus J. And we can look at a graph of this. This is essentially what this looks like. So this is our plane intersecting with our first octant. This is our gradient vector, 1, 1, 1, pointing out of the plane. And then in the XY plane, we want it to point down because this is our region underneath this triangular slab here. And we don't want it to point up because that would point into this region. We want it to point outward. And so it would have to point down. Same thing, this is our YZ plane right here. We would want it to point backwards to negative X so that it points out of the region. And then this is our XZ plane. Again, we want it to point outward away from the region interior. And so that would have to point in the minus Y direction. So these are all orientable surfaces. We can orient them either outward or inward, upward or downward as we need to. Now, not all surfaces are orientable. And so this will sort of be where our calculus will break down and we'll have to, do other kinds of weird things. But the classic example of a non-orientable surface is a Mobius strip. So there's an example of one. You can create one very easily by taking a strip of paper and then twisting one end a half a turn over so that the back side is now on the top, and then tape the pieces together. And then you can see what this is like. The issue with the Mobius strip is that when you calculate the normal to the surface, you can be on this position on the surface either at one of two different places, and you don't actually know, depending on how many times you've gone around the loop, whether you're pointing outward or whether you're pointing inward. So if you travel along it one time around, you'll be on the outside. But if you go around one more time, then the same point, you'll be at the same point, but you'll be pointing, your normal will be pointing in the opposite direction. And then it'll flip again if you go around the Mobius strip one more time. So this non-orientable surface will create problems for doing surface integrals, and that's bad. But all of the problems that we generally work with in multivariable calculus are all orientable surfaces, and there is a way to specify either inward or outward or upward or downward as needed for the given problem.